In this section, we're going to use the fundamental theorem of calculus to evaluate some definite integrals. So here we wrote out the fundamental theorem of calculus. Let's look at the first part. We defined this notation to represent the area, the shaded area over here. That's the area under this curve, y equal f of x, from a to b and above the x-axis. And the fundamental theorem of calculus says that that area is actually related to the antiderivative, and is in fact equal to the antiderivative of little f evaluated at b minus the antiderivative evaluated at a. And this is the second part of the fundamental theorem, and we saw that this second part really comes from the first part. But let's look at this first part again and just quickly remind ourselves of the sketch of the proof. So we said that we proceeded to find the area in the following way. We found the area by breaking up the shaded area into rectangles. Let's say this is one typical rectangle. We broke it up into many narrow rectangles. Okay, let's say quite a few of them, where the top of each rectangle hits the curve, the top left corner, say. Now let's say this particular rectangle, let's say it's the base of the rectangle goes from x1 to x2. All right, so this point right here is x1, comma f of x1, because the top of that rectangle hits the curve. So this line over here has length f of x1. So the rectangle has area f of x1 times x2 minus x1, x2 minus x1. All right. Okay, so if we break up the entire area into these rectangles, we said that this sum all right, the area of each little rectangle f of xi, xi plus 1 minus xi. If we sum up the areas of the skinny rectangles, we get an approximation of a. All right, so our sum is going to go from 0 to n minus 1, assuming we have n rectangles. Well, this sum, if we keep on increasing the number of rectangles, that is, if we take the limit as the number of rectangles goes to infinity, we define that limit to be whatever is represented by these symbols. We use this notation to represent this limit. So this notation then is the actual area. Now where does the notation come from? It comes from the sigma is a Greek letter S, and here we have an elongated S, so we replace this sigma with this elongated S in the limit. And here we have these I limits. I starts at 0. When I is equal to 0, x of I is a, to n minus 1, okay, which would be the x value right before b. So instead of writing I equals 0 to I equal n minus 1, we go from a to b. All right, so this represents the actual area. And the way we showed that this actual area is equal to the antiderivative at b minus the antiderivative at a is by simply replacing in this sum, replacing f of xi by an approximation in terms of the antiderivative. So the approximation was the antiderivative at xi plus 1 minus the antiderivative at xi over xi plus 1 minus xi. Now where does this approximation come from? Well, remember, this is the slope of a secant line. the slope of a secant line is approximately equal to the derivative. Little f is the derivative. If these two, xi and xi plus 1, are close to one another, then it's very close. The slope of the secant line and the derivative evaluated at x sub I would be very close. So that's the approximation that we used. And we saw that when we do this, this cancels the denominator, and then we have a lot of canceling, and we just end up with f of b minus f of a. Those are the only terms that do not cancel. So that was how we proved the fundamental theorem. In number 1, we want to find the area under f of x equal x plus 3 and above the x-axis from x equal 1 to x equal 4. So here we have a picture of the area. It's this area right here. All right, and here we have the line, y equal x plus 3. And we're looking at the area underneath and above the x-axis. So we want to first use geometry formulas to find this area. So let's divide this area up into a rectangle and a triangle. This rectangle has base 3, length 3, and height 4. So the area is equal to 3 times 4. 12. And let's look at this area of our triangle. It's 1/2 base times height, so the base is 3. The height goes from 4 to 7, so that's also 3. All right, 9 over 2. And so the total area is equal to 12 plus 9 over 2. That's 33 over 2. All right, so that's part A. In part B, we want to find the same area using the fundamental theorem. So we're just going to integrate from 1 to 4, x plus 3. Use the power rule, and we have x squared over 2 plus 3x. And we're going to substitute in first 4, so we have 16 over 2 plus 12. And then substitute in 1, we have 1/2 plus 3. So that's 16 over 2 plus 24 over 2 minus 1 over 2 minus 6 over 2. And this comes out to 33 over 2. In number 2, we want to find the area between this curve and the x-axis. So this is a parabola that faces down. So let's visualize the area would be something like this. That's the x-axis, and that's our parabola. So we need to find the limits of integration, or the places on the x-axis where the parabola intersects. All right, so what we're going to do is just simply set this equal to 0, find the x-intercepts. All right, let me just multiply both sides by -1. So we have x squared minus 2x minus 3. and factor. And here we have x minus 3, x plus 1. So the intersection points are 3 and minus 1. So to get this area, we're going to integrate from minus 1 to 3, minus x squared plus 2x plus 3. All right, we'll do the power rule. Here we get 2x squared over 2, so I'm just going to write x squared because the 2 cancels with the 2 in the denominator, plus 3x. And we'll evaluate between minus 1 and 3. Start by substituting in that 3 over there. We have minus 27 over 3, plus 3 squared plus 9, plus 3 times 3, that's plus 9 again. Substitute in minus 1, and here we have a negative, so we get 1/3, plus 1 minus 3. Okay, here minus 27 over 3, that's minus 9. Minus 9 plus 9, so here we just have 9. And here we have 1/3 minus 2. One-third minus, let's say 6/3. So we have 9 plus 5/3. All right, so I'll just change the 9 to 27 over 3 plus 5 over 3. So we end up with 32 over 3. And number 4, we're evaluating this definite integral, the integral from 1 to 2 of 1 over square root x. So first we want to rewrite, because we want to rewrite this because we want to use the power rule. So 1 over square root of x, we're going to express that as x to the minus 1/2. Okay, now we'll just do the power rule. Add 1, add 2 over 2, and we get x to the 1/2. And then we have to divide by 1/2, which is multiplication by 2. And now we're going to substitute in these limits of integration. So if we substitute in 2, we have 2 square root 2. And now substitute in 1, and we have minus 2. All right, so that's that, 2 square root 2 minus 2. In number 5, we're using the second part of the fundamental theorem. Let's just remember what that is. So it says that the derivative with respect to x of the integral from a to x f of t dt is equal to just f of x. So that's the situation we have here exactly. Here, this is our f of t. So all we do over here is write down this function and replace t with x. Okay, let's look at the second example, b. This is slightly different only because we have, instead of x here, we have x squared. So we're going to be using the chain rule. When we take the derivative, we're going to replace t with x squared. And then we have to multiply by the derivative of x squared, that's 2x. Okay, let's just simplify this. Cosine squared of x squared let's write, first of all, I'll put the 2x in front, and we can just write cosine x.